Welcome. So today we're going to be talking about this book, which is Engineering Systems, Meeting Human Needs in a Complex Technological World. It was published back in 2011, but it's very good. I've read it multiple times, hence so many little tags. There's so much knowledge in this. It's a short book. It's about 200 pages long, but it's filled with great knowledge, and there's so many references in every single chapter that if you want to delve deeper into any more topics, you can follow them off. So yeah, published back in 2011. It's 2024 now, so about 13 years old. But there's plenty of good things in there that you would want to continue to learn from. So the authors, we've got Olivier de Weck, Daniel Roos, and Christopher Magee. All three of those are professors at MIT, but with slightly different specialisms, all within engineering. So Professor de Weck is aeronautics and astronautics, MIT. He's also author of the Technology Road Mapping and Development book that I think many of you are aware of. And myself and Ollie, we co-lead in COSE's Future Systems Engineering Foundation's research project, which should have some good papers coming out soon. Then Daniel Roos, he's famous for being the co-author of The Machine That Changed the World. So those of you interested in Toyota Production System, lean manufacturing, that's of course the very famous book on that topic, released in the 90s, and well worth looking at if you haven't before. And then Christopher Magee, he's famous for focusing on theories of technological change, including some analysis of patents and scientific paper networks. Great. So for this book, I think the key thing we really need to understand is what is an engineering system, and then how is that different from systems engineering? Because if we don't get that clear in our minds, it might be very confusing, which won't be very good. So as defined by the book, an engineering system is a class of systems characterized by a high degree of technical complexity, social intricacy, and elaborate processes aimed at fulfilling important functions in society. So let's take the emphasis on the interaction between technical components and human/social elements, and to build and maintain something like that, an engineering system, would require a multidisciplinary approach. Now in the book, they give an example of a mechanical watch, like this sort of thing, which in the book they refer to as a technical artifact, not an engineering system. Equally, something like a commercial airliner, that they would refer to as a technical artifact, but the commercial air transportation network, which includes in it air traffic control, individual aircraft, the organizations that own and operate them, that would be an engineering system. And so other examples of engineering systems would be healthcare system for a country, energy grid, and things of that nature. So if you've got that in mind, that definition of the engineering system, so a class of systems characterized by a high degree of technical complexity, social intricacy, and elaborate processes aimed at fulfilling important functions in society. Now let's think of how that's different than systems engineering as per the book. So first of all, they explicitly state in the book that they're not the same thing. So I'll quote directly from the book. Given that they're similar names, that's of engineering systems and systems engineering, we are frequently asked whether there are differences between systems engineering and engineering systems. While they have an important relationship, they're decidedly not the same thing. So we need to keep that frame in mind as we review the book, that engineering systems and systems engineering are not taken to be the same thing. As per the book, they say systems engineering originated in industry and government sectors in the 50s in the response to the needs of large-scale projects such as those in aerospace. And I think that's pretty uncontroversial. Most people would accept that. as a history of where systems engineering came from. Now, they refer to the primary focus of systems engineering being around that of systems engineering is primarily concerned with the product and its customer and end users. Other stakeholders and external factors are typically of secondary importance, reflecting a narrower focus when compared to engineering systems. So we remember with that definition of engineering systems, it was very important, this idea of social intricacy and that sort of emphasis between technical components and human and social elements. Now, additionally, consideration of ilities and externalities. We'll talk a bit later in sort of more detail as to what they mean, but it might be a good way of just touching upon this, and later we'll continue. So, systems engineering often takes a limited view of ilities, and by ilities we're talking things like reliability, maintainability, sustainability, and may not directly consider the externalities, sort of environmental impacts being a classic example. And existing government policy and regulations in systems engineering are treated as fixed constraints, whereas in engineering systems, they're viewed as things to be adjusted based on an interaction with the policymaker. And so then the interaction with social sciences, systems engineering typically minimizes the role of social sciences and more focused on the analytical, quantitative, and technical approaches. So, summarize that. So, engineering systems is focused on a broader integration of systems with societal and environmental contexts, and considers the sort of human, organizational, and societal factors as very integral components. And sort of by definition of an engineering system, it has to include that. Whereas the relationship with engineering systems, where the relationship with systems engineering, so even I'm getting a bit confused here, is one of where systems engineering can deliver a technical artifact that is of high quality and works, but that may well be embedded with others in your engineering system, which is that broader system that encompasses the social and technical systems. Okay, so that's as per the book, me sort of summarizing what they say. Where I suspect, this was written in 2011, things have changed. Systems engineering in itself is an evolving discipline, and I think there would be plenty of people who would say that some of those ideas that are being conveyed as being that of engineering systems are also being addressed by systems engineering. I'm not taking a stance either way on that. I think that gives us a nice sense of the difference between an engineering system and systems engineering. Now, before we kick off into sort of the more detail of the book, if you haven't already signed up to the newsletter, you should go to www.joshuasutherland.com, and there's normally a free offer on a training course. You should get that, and yeah, there'll be a link in the notes below which you can sign up on. Right, so let's get into how the book is laid out. So we've got 8 core chapters. The first being chapter 1, From Inventions to Systems. And in that, they describe 3 big epochs of technological development in the human race, and they map onto that as time passes, the world population. So we have an epoch of artifacts and great inventions, and an example of that would be the car. Epoch of complex systems, where an example of that would be highways. So we built cars before we essentially built paved roads, especially high-speed paved roads. And then the epoch of engineering systems, where we have a transportation system, things like topics like smart motorways, and where we're integrating this is a transportation system with software and things like that for the stated purpose of high performance. Chapter 2, what is an engineering system? So in this video, we've already sort of talked upon that, but it's describing what is an engineering system, because I think it would be easy to categorize this as the same as systems engineering, and they're clear that that isn't the case. Then chapter 3, rethinking about systems. So this describes the iterative nature needed when dealing with engineering systems, problems, and opportunities. And they describe their approaches to how to work with them, whether that's maintaining existing ones, evolving, or developing brand new ones. Chapter 4, so this is our Ilities, so life cycle properties of engineering systems, and why they're so important. So that's reliability, maintainability, sustainability, safety. Here there's I think we can come up with at least 50 different ones, and some of them will be more important than others. Chapter 5, modeling and analyzing engineering systems. So provide some methods, tools for doing that, whether they be in various different ways. Okay, chapter 6, partially designed, partially evolved. Again, they place their emphasis on how these engineering systems, they will have very long lifespans, and so will be evolved. Ideally, they would have been designed up front such that they can be evolved. But even if they weren't, it's highly likely they will be. Then chapter 7, engineering systems research and education. So the authors, all being professors, are describing the education and research environment for engineering systems and how those can contribute to it. Then chapter 8, what the future holds. So predictions, trends, and the importance of this. Okay, so if we jump straight to chapter 1, from Inventions to Systems. So the key point here is providing a historical context for how we've got to engineering systems, and in particular these three big epochs. So the first one being that of artifacts and great inventions, and examples they provide being the car, automobile, in sort of late sort of 1880, 1890s, I think, that type of stuff. The telephone, light bulb. So these were all, literally great inventions by anyone's measure. Then we moved into the era of complex systems. So that was of the highways, so sort of the 1930s, 1940s, when the first highway network, into the 1950s, first highway networks were created and then expanded out. So that would be for the car. The telephone, maybe invented in 1876, but you couldn't make calls across a country until sort of a wider network had been developed, and so that would be the telephone network would be the equivalent of the complex system for that data system or communication system. And then the epoch of complex systems, so the progression for the light bulb, we invented the light bulb, and then we developed the electrical power grid, such that people could have energy in their home to use those light bulbs. But then into the epoch of engineering systems, so those highways have then morphed into transportation systems. You think of a container being loaded in a factory, and then that container goes to a port on the back of a lorry or a truck, or on a train. And then gets on a ship. That ship then goes across the world and then is unloaded onto another lorry, for example. And with the telephone network, we know that that's now evolved into to the internet with satellites and various sort of communication systems, which are all interconnected and interdependent, and then that the electrical grid is now evolved into the whole energy system, where, for example, the gas pipelines and things that feed power stations are coupled to that of the electrical system, and those things are not independent anymore. And all the while, the world population has been increasing. And so if we come back to the title again, engineering systems, meeting human needs in a complex technical world. I mean, the fact that the world population has increased sort of implies that human needs are being met, more humans are existing, and evidently they're not facing starvation and these big problems. And it could be inferred that as a result of these ever more extensive systems, that more people are able to exist on the planet when we come to things like agriculture and providing enough food, things of that nature. And then one sort of quote they provide from I guess what would be the former dean of MIT School of Engineering, Subra Suresh. Most of the greatest challenges engineers face in the 21st century involve fixing the successes and of the greatest achievements of the 20th century. And this is quite interesting because if you think like about cars, about automobiles, traffic jams were at least a lot less common before we had cars. Now, they of course did exist with horse-drawn carriages and things in big cities like London and New York City. But as we've have more cars, we now have more traffic jams, and so that is a problem of essentially the 20th century that the 21st century needs to solve, in that being able to have people live in cities and not spend vast amounts of time traveling or not traveling, being stuck, and likewise the burning of oil in the cars and the environmental effects of that. That was not a consideration or not a problem of when there were only a few cars, but now we have a lot of them, and in concentrated areas that causes health impacts. But equally did solve the challenges of all of the waste of horses and just even caring for all the horses that had to exist in the big cities in Victorian times and things of that nature. Okay, so that was chapter 1, and there's some very nice diagrams in chapter 1, in particular sort of this, which shows the that evolution and maps onto it various different artifacts, complex systems, and then engineering systems. So then on to chapter 2, what is an engineering system? We've already spoken about that and the definition earlier. The key takeaway there was that the mechanical watch that they provide an example as a technical artifact, not an engineering system. That an engineering system is a class of systems characterized by a high degree of technical complexity, social intricacy, and elaborate processes aimed at fulfilling important functions of society. So the watch, it doesn't on its own fulfill important functions of society, and it doesn't have high social intricacy that an individual master technician or craftsman can and did and does create such things on their own, and that I can own it and operate it unto myself, and I am not as an individual an important function in society. So then what are the additional characteristics of an engineering system? It exists in the real world and is artificial. So the questions to be asking around that is, if you have a system and you want to know, is it classed as an engineering system? Does the system manifest itself in the physical world? It's not just software. It can include software, but it needs some hardware there as well. Has the system or part of it been created by humans? Or does it exist completely in the natural world without human intervention? So the sun and the planetary bodies, they would not be considered an engineering system because they were not created by humans. So it has dynamic properties in hybrid state. So the questions to be asking there is, do any of the system's properties change with time? And are the system states a mix or both continuous and discrete? Yes, essentially engineering systems are not static. And there's some human control. So does the system have elements that are at least partially controlled by humans, while others may function autonomously? So if you're answering to yes to the bulk of those, then it's fitting with the definition, then likely you have an engineering system there. Now, for additional classification, they provide a very helpful table of processes and operands, such that you can classify a particular energy system into one within that 5x5 grid. So 5 different processes, fundamental processes, and 5 different fundamental operands. So that likely is hard to understand without looking at it. So I'll just bring it up on my book. So if you imagine a table, and I think this is on Ollie's road mapping website at MIT, but we can think of so things in which we can operate on, these operands being living organisms, matter, energy, information, and money, and the processes that we can perform on those operands being transform, transport, store, exchange, and control. So let's take a very easy one. Let's take the process of transport, and we're operating on matter. So transporting matter, we could use a train or a car or an aeroplane, a ship. But then if we think about if we want to transport, but we're going to transport energy, then we would have an electricity grid would be one such example. And so across that 5x5 grid, you can classify what your particular engineering system is operating on. And let's just pick one more. So if we would like to for information, and we want to exchange information, so the process of exchange and the operand of information, then the World Wide Web is another example of that. But yeah, you should really check out that grid. It's very helpful. So then on to chapter 3. So rethinking systems. Now the key idea here is that when dealing with these, with systems problems in general, but in particular engineering systems, we need to have a iterative approach, that it is not possible, there is too much uncertainty, too much unknown, to have a very simple step-by-step approach where we go from our first analysis of the problem to our first development of the solution, so that's done. It is likely that as you build the solution that you're going to uncover problems that were not otherwise known and go back and iterate upon that, whether that's in the design or in the actual built one. Now, they also stress the need to observe the problem and the potential solution, the engineering system, from different perspectives. They provide 4 very fundamental ones. So scale, function, structure, which some might refer to as architecture, and temporality. So scale being, are we looking at a very zoomed out view? You could imagine a map of a country and the road network. We could really zoom out and we can just see the big roads, or we zoom right in and we can get right down to the selection of the particular type of road surface. The function, so this is a different description. So what is the functionality that the system needs to provide? The structure, so another example of structure would be that road network, how the roads are connected together and to which towns and cities. And then temporality, so how is this thing changing with time? This engineering system is changing with time. Now, to make it even more difficult, we have complex causality. So our engineering system very likely is by definition not simple, and there is strong interactions, bidirectional interactions between different aspects and its environment and those that interact with it. So then on to chapter 3, life cycle properties of engineering systems, so the Ilities. Now these are stressed as being incredibly important for engineering systems. So if you're not familiar with the term Ilities, it might be easy to illustrate, for example. So reliability, maintainability, sustainability, flexibility, safety, usability, resilience, interoperability. So the bulk of those have that Ility at the end. And they refer to essentially non-functional requirements of the system. So these are not the aspects to what the system must perform. They are more descriptors of the longer term, well, not necessarily longer term, the aspects of the system. I want to say how it does it, but that's not quite right. Essentially it's an emphasis of the system not simply just working, but that it has properties that are successful for the system to not have negative side effects, and whether they be to the wider environment or to itself. So by that I mean, so with reliability, if we design an engineering system or even a technical artifact that is unreliable, then it will not function at the amount of times that potentially it is expected to do. And we might consider that's okay, but that is one such Ility. But then maintainability. We could design a system that does fulfill all of its functions. It might even be reliable, but it might be incredibly expensive or difficult to maintain. And they give an example of, I think it's the F4 Phantom, which flew over the Vietnam War, and how its replacement, what the F4 Phantom was considered, it wasn't unmaintainable, but was very expensive to maintain for the amount of every hour of flying, versus the replacement, which was the FA-18, which was explicitly intended to be maintainable. And so all of these Ilities are likely important, but of course you're going to have to focus on what is the real importance for your particular engineering system. But it's this emphasis that simply working is not sufficient, especially given that we've already said that these engineering systems are sort of meeting human needs, and that they are very they're fulfilling very important functions in society, and thus these life cycle properties are considered very important. Then on to chapter 5, modeling and analyzing engineering systems. So as many people likely know, there are a whole raft of tools and methods to do analysis, engineering analysis. But we need to remember that their ability to predict sort of systems behavior over very long time spans, particularly when we've got social aspects, human aspects, which are intrinsic to an engineering system, their power of prediction is going to be limited because there is just so much uncertainty. However, they do describe some sort of classic approaches that people are likely familiar of. So using abstraction, using model-based systems engineering, particularly they use OPM, object process methodology, system dynamics, so causal loops, things like this, matrix techniques. But they do emphasize the need to define the problem space, the scope, especially on an engineering system. It could be easy to start with the energy network of the United States, and it expands to add in Canada, and then you start to say, well, is environmental impacts important, and then the whole globe's included, and it gets about out of hand. So that's going to be a bit of an art rather than a science, knowing what scope to hang on to. Okay, then chapter 6, so partially designed, partially evolved. They provide 4 big examples where engineering systems that have been partially designed and partially evolved. Toyota production system, given the involvement of the authors with machine that changed the world. This is clearly very important, and it is a system that has itself evolved and is used to evolve Toyota's vehicle line and manufacturing processes. The Boston Big Dig, as many people would know, where now in downtown Boston you have a big park, and it used to be a very large flyover motorway, which is now in a tunnel, and that might at first glance seem to be the type of thing that would have been architected up front and then built, but they came across many challenges as they went through the program and had to evolve. But then two classic ones where they have evolved would be the electrical grids, particularly in countries that got electrical grids earlier. In particular, sort of the northeast US, when we had the battles between AC and DC, Thomas Edison and Westinghouse with Tesla, and I'm sure some other guys as well. That wasn't that evidently now is an engineering system. How much sort of flexibility they had built in such that it could be evolved, I don't know. I have to look into that. But it is something that has evolved. In the fact, DC is now no longer used. We use AC and nuclear power stations, wind turbines, solar panels. All these things have been sort of added into it that didn't exist at the time of the original grid. And new cities and suburbs get built out, new factories get built, and so they have to be connected to it. But then the internet, the internet was explicitly designed to evolve, and it has evolved massively. I imagine much more beyond even what the original architects would have thought. The amount of data that transfers, the SpaceX Starlink low Earth orbit constellation for internet. The fact that the International Space Station, I believe they have internet access, and so that is evidently something that has evolved. So what we just need to be very clear that engineering systems have to be seen as things that get evolved. But then additionally, we have to think of the whole engineering design process, particularly for large-scale systems, which involve a lot of people. It is unto itself a socio-technical process. And I don't know if we could consider it an engineering system, but we have to at least pay close attention to that. So things like flexibility, in terms of those life cycle properties is likely a very important one for engineering systems. Okay, so that was chapter 6, partially designed, partially evolved. Now on to chapter 7, engineering systems, research and education. So the authors provide a history of engineering education, which is very interesting, and sort of describe how at least two cultures have sort of ended up separating, so technologists and humanities being separated, which is unhelpful for solving the challenges of engineering systems. And to successfully deliver engineering systems, we need to have skills that cross that bridge. And so they describe some programs out there in the world that you could attend that are attempting to provide people who have those cross skills. And they talk about CSUN and sort of a collection of universities that are all interested in engineering systems and doing research upon them. And I think I've given a presentation there once before. Okay, so chapter 8. What does the future hold? So they sort of talk of potentially a bright future for the human species if we are to get a grips with engineering systems and deliver them successfully. If we're to avoid that decoupling of technical and social thinking, we can make policy with an understanding of the technology that's involved, because if we don't, by making policy without an understanding of technology, like that's a recipe for disaster. Then I'll read a passage directly from the book, which I think is a very nice way to sort of conclude at least sort of what that future could be. So the interactions within these large-scale complex socio-technical systems, as well as their interactions beyond the system boundaries, raise yet more challenges. Engineering systems have complex causation relationships, and the analysis of complex engineering systems must rest on the foundation of bidirectional causation and considering all feedback relationships that exist. Further, unlike with artifacts, the life cycle properties of these systems are crucial. These desired properties of systems often manifest themselves after, even as long as centuries after, a system has been put to initial use. Engineers working on socio-technical systems who fail to consider them utilizing life cycle analysis do so at considerable peril. System performance may well come down to these properties because the wide impacts engineering systems have invite far more scrutiny from diverse stakeholders with whose minds the primary functional requirements may not be foremost. So what that's saying is, frankly, is very, very difficult. We've got a very complex set of drivers and interactions, and we need to consider that throughout time while considering all of these life cycle properties. So it is a big challenge, but that suggests there's a lot of opportunity there if one is able to develop the necessary tools and techniques to be able to address that. And then they provide, I think, what is quite a famous list of National Academy of Engineering grand challenges. There are other grand challenges that have gone out there. I know DARPA has had some and things like that. And they use them as examples that they would all require engineering systems to be delivered on. So making solar energy economical, you can think of building out an electrical grid that's able to support distributed energy production like that, providing energy from fusion, developing carbon sequestration methods, that's carbon dioxide being either removed from the atmosphere or avoided going into the atmosphere after we burn a fossil fuel. Then I think some examples of this is they use it to be pushed back into disused oil wells and gas wells. Manage the nitrogen cycle, so that's to do with fertilizers and things. Provide access to clean water, restore and improve urban infrastructure, advance health informatics, engineer better medicines, reverse engineer the brain, prevent nuclear terror, secure cyberspace, enhance virtual reality, advance personalized learning, engineer the tools of scientific discovery. I think those are all pretty interesting to be working on. They don't talk about space travel. It's interesting. This is back in 2008, so maybe there's an update that would include something of that. And they also give the example of IBM, which I thought was interesting. So IBM, as we all likely know, started off as a hardware company making things sort of mechanical calculators, and then moved into making computer hardware, whether it be big mainframes, and then onto the personal computer. And famously, Microsoft were the ones to make the operating system for it. And now IBM is sort of viewed as an engineering system company. This isn't mentioned in the book, but I think IBM at least operate the system by which in London, if you drive into central London in a personal car, you have to pay a fee, congestion charge, to apply a cost to you contributing to traffic congestion. It's about £15, about $20 per day per vehicle, I think. And at IBM, I believe, operate that. And so that, I'm not going to say that's necessarily an engineering system, but it's somewhere that's approaching that, where you're trying to manage the transportation of a major city, and evidently that then interacts with the rail system and the bus system, and that it's disincentivizing driving a car, and which would then make taking the train potentially be the better alternative. Okay, so then what's also very helpful is there's a whole appendix of terms and definitions, multiple pages of this. I think it's pretty helpful. Yeah, so you've got definitions of all those ilities. Flexibility, evolvability, agility. I'm just reading from here. Robustness, scalability, modularity, extensibility, fail-safe, safety, durability, sustainability, quality, reliability, repairability, maintainability. And then lots of other definitions. Interdisciplinary, involving two or more academic disciplines or professional practices. I'll pick another random one. Cybernetics, originated from Robert Wiener. Models, systems using feedback processes. Pick another one. Interaction, the property of entities that exchange something material or immaterial that constitutes or contributes to their interdependence. So yeah, I think this definition is very helpful. I'm quite involved at the moment doing some definition stuff in Cose regarding complexity, and it is very helpful when authors in anywhere define their terms very clearly, even if we disagree with them, having them defined there. And so the definitions are version 17 of MIT's Engineering Systems Division. And I think you can find the previous versions on the internet if you use Google. So some conclusions from here, from my words then. So I guess if you wanted a comprehensive overview of engineering systems, not systems engineering, engineering systems, this would be the book. It's short. There's about 200 pages, and it offers a very thorough exploration of that topic, and sort of emphasizing their socio-technical nature and need for a multidisciplinary approach. It's distinct from systems engineering, while related. Engineering systems and systems engineering are distinct. and engineering systems focus on integrating the technical and the social elements with those broader societal contexts, whereas systems engineering is more narrowly focused on technical design and optimization. Could be considered engineering systems are critical for addressing global challenges like those I listed from the US National Academy of Engineering Grand Challenges. Access to clean water, so building water networks, energy sustainability, cybersecurity, things like this. It's a very future-orientated discipline. We can see that this type of engineering is likely to grow and to be ever more important. And I think we just need to emphasize this need for the socio-technical thinking. I might say go beyond thinking and doing, achieving, delivering, but clearly important. And one little quote I very much like in the right at the beginning. So this is the authors talking. One of our major premises is that the co-design of regulations and policy with new technological systems must be the new way of designing these systems. I think that's very interesting, because if we think of many sort of examples in the world where big engineering projects have got tied up in regulations and trying to meet regulations, that might be important regulations to meet, but it could be better to have those regulations explicitly evolve as the project's going on, when we discover what is actually important, and we essentially have reduced the amount of uncertainty as we move along. I hope you found this interesting and useful. I guess some questions to think about would be, since the book was published in 2011, how have things changed? Like, does this just simply mean be the same, or have things changed? I mean, key idea I would have is that, and it would have been predicted at the time of this book, but now we have very high bandwidth data essentially everywhere. I own one Starlink dish and another on another facility. So you essentially, and OneWeb, and maybe there's some other of these low Earth orbit internet service providers. That, I think, is a sort of enabler of these ever more extensive engineering systems. But even just mobile phone 4G type stuff, this is sort of everywhere, and a lot of manufacturing equipment now has 4G antennas built in. Cars do, maybe in 5G, such that they're sort of always communicating with people who would need that information for maintenance. I hope that's been good. As I said, subscribe to the newsletter. Go to www.joshuasutherland.com. Subscribe on YouTube, and I think on the website as well, it describes how you can subscribe to the podcast off of YouTube if you prefer that. I think there's RSS feed. Great. So leave your comments, and see you later.